All right, welcome back. In our last video, we had started our discussion of concrete materials and some of the properties and the manufacture of that, and it started going through a lot of the characteristics of those. And due to length restrictions, I decided to go ahead and stop it there and to make a follow-up episode that will continue our discussion from last time into other concrete material properties, and then we'll also spend the rest of this lesson talking about the steel reinforcing characteristics as well. So next up on our list of materials properties is the concept of creep, and we've kind of talked about creep a little bit already, but what creep is kind of a continued deformation of a member whenever it's subjected to a sustained load. It could be a dead load or any sort of long-term loading effect. And what we have are some typical creep parameters, and there's a large variation in these numbers usually. This is just to kind of give you a sense of the magnitude or the order of the actual coefficients. But you can see that, relative to the concrete strength, that as the concrete gets weaker, you get more and more deformation associated with stress. And again, if you look, the units are kind of interesting. This is 10 to the minus 6th strain per psi. Okay, and that's the creep that's associated with it. And then we also get some corresponding creep coefficient factors that show up here. Now, like I say, this is more just to kind of illustrate the magnitude of the values and how they vary with higher strength concrete. So you can see that if we get down to like 10,000 psi, our coefficient is 0.28, but if it's only 3,000 psi concrete strength, we're nearly 4 times that value at 1.0. So it's there's some pretty significant differences, especially in the lighter strength concrete values. Okay, the table that really matters to us though is the next one, and so we'll talk about that as well. Okay, and so here's what we have. Okay, kind of as a rule of thumb, what we do is we're looking for this time-dependent factor associated with the creep of concrete. And so what this is basically a ratio of the strain associated with creep versus the strain that's associated with the instantaneous load. So if I put a load on a beam, what happens, if I start to kind of look at this, if I put a load on the beam, it's going to get some sort of deformation on its own. Okay, and that's this delta amount here. Okay, but what happens over time is if I hold this load on a concrete beam over time, this deflection continues to grow in magnitude. Okay, so the instant strain is the one associated with this first loading or this first displacement. Okay, the creep then is the total beyond that that's also included. And so they've come up with some methodologies for how can you estimate this. And so to kind of help us, again, this is just kind of a rule of thumb, and I have a lot of these are just kind of based on practical experience and some industry practices and those kind of things, maybe not so much ACI factors, but it kind of gives you kind of a sense of it. So what we have here is we have a beam that is loaded, and we kind of take a look at what's happening to the strain of this thing as time goes by, because creep is a time-dependent phenomenon. Okay, and so you can see I've got from starting at 0, I go out to 700 days, so that's basically 2 years out. You can see that in the life of a beam for a sustained load, you can see that I get some sort of instant load. If I put the load on to this point here, it's fairly linear, and that's the strain that's associated with that instant deformation. Okay, and then I hold the load on this thing, and as time marches on, the strain continues to move up. Now, it's not a linear phenomenon, okay? It kind of keeps building up, and then at some point, what we do is we remove the instant load, okay, and take it away. And what happens, I get an immediate drop of that amount, which is the same as what we had over here. It drops down a certain amount, okay? And then I get a little bit of what we call creep recovery, because I've reduced the stress in the member that caused this original stress, so I get a little bit of that back. But what you notice is that it never comes all the way back. Okay, and so this is kind of an unloading phenomenon and a reloading phenomenon. That this is basically permanent strain in the beam. I could take all of the load off to get me to here, and then it would rebound a little bit, but then I've got permanent deformation associated with creep. And basically it's a rearrangement of the molecules in a concrete member in such a way that they don't ever come back. And then, just for a good measure, we can reapply the same load on it, and it jumps back up that instantaneous amount, and then it starts to creep again a little bit. So it's kind of an interesting phenomenon that starts to happen. So what we want is we want a way to be able to kind of estimate this coefficient. Okay, and so the equation that we use is t to the 0.6 power divided by 10 plus t to the 0.6 power multiplied by that c sub cu factor. And this was that factor in that last table that I showed you. Okay, and it basically boils down to that at a time of 1,000 days, okay, and a CCU factor of 2.9, okay, the time-dependent deformations associated with creep has a factor of 1.9, meaning that it's nearly double what we were getting on the instantaneous. Okay, so it's double the amount of the initial loading. So, if my delta is 1, okay, then my delta total on this is now equal to the 1 of the original plus the 2 from the creep would be a factor of nearly 3.0 times the deformation. So they're not insignificant deformations that have to be kind of considered as we look at this. All right. So that's the first of our phenomenon, and we'll talk a lot more about this when we get into deflections and serviceability calculations a little bit later on in the course. But that kind of opens your eyes to some really unique behavior that is associated with concrete. Now, you do get creep in other materials. Steel will creep a little bit. You get a relaxation in pre-stressing tendons on those, and they're all kind of creep phenomenon. But it is much more pronounced in concrete than it is in any of those other materials. So that's our first one. Our second one then has to do with shrinkage, okay? The shrinkage of concrete. And what this is basically, it's a volumetric change, okay, that is unrelated to applied loads, okay? And a lot of this has to do with, a lot of shrinkage occurs as a function of like surface area. You'll notice that like if they pour a sidewalk and they don't cure it correctly, that you can get micro cracking in the top surface of a slab just because the concrete at the top behaves differently than what's down inside of that particular slab, just by the nature of the curing and those processes. And so shrinkage is something we're trying to kind of provide. This guy will generally dictate some amount of minimum steel in a slab in a direction that may not be associated with the load. So just like what we had with the creep, we've got a rule of thumb for shrinkage. Okay, and the formula that we're going to use is that it's T divided by 35 plus T multiplied by this ultimate shrinkage strain. Okay, and again, this is a highly variable factor, and what we do is for average normal conditions, nothing too out of the ordinary, we're going to take a guesstimate on this epsilon value of being 0.0008, 8 times 10 to the minus fourth for average conditions. Okay, if you get into unusual conditions, then you've got to do your homework a little bit differently, and again, we'll talk a little bit more about that, but for now, that's the value that we're going to use. Again, T is measured in number of days, okay, and so what you'll see is that the shrinkage strain on this is going to vary between about 0.0002 and 0.0007 is kind of the range of values that will show up based off of the time. So early on it's this value, and then it's going to grow to that. Okay, and what happens is when you shrink a section, if you think about it, if all of a sudden this guy wants to shrink back a little, then I'm going to start getting cracks kind of down the middle of this thing, and that's what shrinkage is going to do, and that's what happens in the surface of slabs and sidewalks and those kind of things. It's hard to totally eliminate this guy, but it is there, okay? And so what happens is it induces tension in the concrete, but at the same time, it can actually put more compression in the steel, and that kind of, as a result, will lead to more cracking. So with all of these phenomenons, the long-term effects and the short-term effects, we can start to design for a total strain behavior that is the initial loading strain, plus the creep strain, plus the shrinkage strain, plus a couple of others, including things like thermal strains. On a hot summer afternoon, you get some extra strain into a surface that's heated up or cooled off as a result, and those would have to be considered as well. And so that's kind of the way that we start to kind of look at this. This is the easy one. That one comes from your structural analysis, but these two guys are actually very significant and need to be also kind of considered when you're looking at your serviceability criterion. And again, we'll cover this a little bit in more detail in a later lesson, but that's our case for the shrinkage phenomenon. Okay, all right. Our next area then that we want to kind of talk about has to do with the reinforcing steel. Okay, so again, reinforced concrete is a combination of two materials. We've talked about the concrete. Now we want to talk about the reinforcing steel properties. And what we have here is kind of your typical stress strain curve for what we call mild reinforcing steel. Okay, and so kind of in a generic sense, if you remember from your mechanics materials or in your material science classes, we can draw kind of the behavior of a steel tensile test. So we're taking, some sort of steel tensile coupon and putting a sigma on this thing, and we're studying what's happening to the strain. Now, on the vertical axis, we're going to plot stress, okay, and on the horizontal axis, we're going to plot strain. And so if I start off at 0, there's a linear relationship that builds up into the proportional limit, or what we idealize as the yield point for mild steel. Okay, and the slope of this line is the Young's modulus value. Okay, remember, because we said sigma is equal to E times epsilon. Okay, and so E is the slope of this line, where sigma is this axis and epsilon is that axis. And then typically steel, we take the E value as being 29,000. Okay, and then for a little while we get this yield plateau where it doesn't get any gain in strength, but it does continue to deform. And this is kind of, if you remember in your material science class, when you've done these tests, you get this kind of necking phenomenon that starts to happen. Okay, and it's kind of, it's deforming for a little while, but it's not gaining any more load. And then eventually it reaches a point where all of a sudden the molecules and the crystals in the steel matrix realign in such a way that they start to provide a little bit more resistance again. Okay, and that gets us into this strain hardening plateau, and it's here where I pick up this maximum stress. Now, it's not the yield stress, it's not your 60 ksi like you learned back in steel class. It's actually some higher value on this, and then it will start to kind of drop off as a result of that. And this maximum stress is assumed to be somewhere around 100 times the yield strain. The ultimate strain is 100 times the yield strain value. Okay, now a lot of times what we do in calculations is we just idealize and say once you hit yield, you're done. Okay, and we completely ignore what's happening up there. So this provides us a little bit of extra safety factor that we don't necessarily count on, and that's good for concrete. It gives us a little bit of a window to work with. Okay, now like we said, the modulus elasticity for steel is 29,000. Okay, and then the maximum strength F max cannot be utilized because it corresponds to an excessively large strain, which means that a structure has to deform excessively to reach F max. All right, this is a very, very large number. If this is our 0.002, which is where yielding occurs, now we've got to go, this is like 0.2 inches per inch. That's a massive, massive strain. Okay, and to get to that level, I'd have to have huge deformations. Okay, so typically what happens is we set the useful strength to be the yield stress Fy on theirs. Okay, now if you recall, for the grades of steel and the strengths that we're going to be looking at, again, we talked about there being a range between 40 and 80 ksi. Currently 60 ksi is by far the most common. Okay, but if you start looking at older structures, okay, 40 ksi was a bit more prevalent up through about the 1970s. Okay, but modern structures is almost exclusively this guy. And even currently they're starting to go higher than that, but this almost always is 40 or 60 ksi. Okay, now the Fy 60 ksi, we're going to call that as a grade 60 steel. Okay, and the 40 ksi is a grade 40. So you can see that the grade number corresponds to the yield stress on this, and this is per ASTM 615. So you can see that in table 6.4 if you want more information on that. Okay, but for us, we're going to be dealing with 60 ksi almost exclusively. All right, now rebar or reinforcing steel comes in a wide variety of sizes that we can take advantage of, and part of the game that we make when we do concrete design is figuring out the arrangement of the bars or the number and quantity. Okay, we're still doing stress calculations, but sometimes you don't need a very big bar, or sometimes you don't have room for a lot of small bars, and you have to kind of, there's this, it's almost an art to how you start to select those. And again, we'll practice with those a little bit. What they do is they take a round piece of steel, and then they're going to deform the surface of this to increase the bond. Because remember, we talked about bond being that interface between a steel bar and a concrete. Reinforced concrete is a combination of two materials, and we got to make sure that they both work together without any sort of slippage occurring between the two. Okay, and so to help with the bond, there are a lot of factors that are included in bond, chemical adhesion, or mechanical interlocking, or some sort of physical deformation. Okay, the deformation gives us a lot of it because it puts these little ribs on the bar, and then the concrete pours in around it when it's wet, and then it hardens, and it gives it something to kind of grab onto. And so these radial rings, if you will, on these bars will provide a little bit of extra strength, as far as helping to preserve the bond value. Okay, Now, deform bars is the most classic, okay, and those will vary in size from 3/8 inch diameter up to about 2 1/4 inch. Now, again, this is a massive bar. This is like a number 18, okay, and it's a huge piece of steel, and there are reasons why this isn't commonly used, okay, but you can see the widespread in the areas of the bars that can be used for, okay. Now, ASTM 615, which is the same spec that we just talked about, okay, which was formerly ASTM 305, okay, basically says that the diameter of a 3/8 inch diameter bar, that's called as a number 3, okay, and then a 1 3/8 inch diameter bar, or 11 1/8 inch, is called a number 11. And so what you can see is that the grade of the bar, or the number of the bar, a number 3 or a number 4, is the number of 1/8 inch increments that make up the diameter, okay, and then ACI has a table that will produce areas based off of these standard specs and these guidelines, and I'll show you that on the next page. All right, so basically the diameter of a bar is the bar number divided by 8, and we'll take advantage of that as well. Okay, now for larger bars, okay, and these aren't very common in normal structures, but they do show up. You know, we get our number 14 is a 1 3/4 inch bar, and a number 18 is 2 1/4. Okay. But like I say, I try to avoid using those because the bonding issues to be able to fully develop that area of steel, they're very, very long, okay? And so, we have serious issues with the anchorage of these, okay? And we'll discuss that more when we get to chapter 6 and start talking about developmental length. Okay. For bars that are greater than a number 10 in size, the nominal diameter also isn't exactly bar size over 8. It starts to vary a little bit as you get to the larger sizes. But for smaller sizes, this is a very good approximation. Okay. Now, reinforcing bars aren't the only type of reinforcing that you'll see. In this class, that's mostly what we're going to focus with. But in other applications, we get into something called a welded wire fabric, which is basically a metal mesh that has longitudinal and horizontal bars. And what this does is this allows you to place a whole lot of bars in one shot, because all of these pieces are welded, and these things come in 4 foot or 8 foot lengths, and you're able to drop in a whole bunch of bars in multiple directions in a hurry. So this is very useful in slab construction, and it's specifically very, very useful in the precast industry, because I can drop in a whole lot of bars and it speeds up my fabrication time. Because again, at a precast plant, you're looking to build beams, get the form set up, get the steel tied, get the concrete poured, and then 18 hours later, remove the beam and start the process again. It allows for quick turnaround time rather than having to go in and tie in every one of these bars separately. It's very, very useful. The problem is that the bar sizes are much, much smaller than the number 3s. They're very, very tiny wires, okay, and then there are specific spacings and those kind of things. Okay, but a lot of that is associated in Appendix A of the ACI code, and then ASTM 8496. Is the governing spec for welded wire fabric. Very useful, but again, kind of beyond the scope of what we're going to be doing here. All right. Okay, so if we look then at this is a copy of a table that comes out of the ACI code, okay? The standard reinforcing bars, the table looks something kind of like this, and you'll reference this, and after you've used it a while, you pretty much memorize a lot of the values, okay? But the things that we're worried about is, here's my bar number, 3, 4, 5, 6, 7, 8, 9, 10, 11. Notice that it skips to 14 and then goes up to 18. It's kind of the standard accepted sizes. Okay, and so we've got our corresponding diameter, and you can see up to about a number 10. It's pretty much that bar size divided by 8, so 0.375, 0.50, so forth and so on. Okay, but what changes then is that the cross-sectional area of this bar is a little bit different, and so a number 3 has 0.11, and number 4 has 0.20, and so forth and so on. So you'll be referencing back to this table to get these values when we start doing our strength calculations here in a couple of lessons. Okay, and then of course we're always kind of worried about the weight of this thing. If you look, a number 3 bar weighs about 3/8 of a pound per foot of length. Take a look at this number 18 guy. That's 13 pounds for every foot. So if you've got a 20-foot long bar, that thing is like 260 pounds. Okay, it takes more than one person to place this bar. This is a problem. Okay, a single individual, not some sort of muscle-bound bodybuilder, professional power lifter or whatever, just a normal construction worker, we can carry 7s and 8s solo. Okay, you start getting up into the 9s, the 10s, and 11s, they start getting a little bit more cumbersome, especially in the lengths that they're dealing with. And so that's something to think about. If you're a small operation, you like the small bars because I can handle those with one person. I don't need 2 move them around or to place them. Okay. Generally, when I do a flexural design, I like to try to end up in like the 6, 7, or 8 range. That just seems to work out the best as far as development and detailing, and avoiding factors like congestion and too many bars in a small location. It seems to work out very, very nicely. But there are reasons to go smaller, and there are also reasons to go larger that we'll also start to explore. Okay. The last topic that we want to talk about then, it has to do with the joint action of concrete and steel. Okay. The coefficients of thermal expansion of steel correspond to about 6.5 times 10 to the minus 6 per degree Fahrenheit. And for concrete, it's 5.5 times 10 to the minus 6 per degree Fahrenheit. Okay, and they're about the same value. So if I heat up this structure, you can see that the magnitude of the effects in the steel and the magnitude of the effects in the concrete should be about the same. So there's a minimal effect on the bond. Because again, what we're doing is we're looking at, if this is my concrete surrounding here, and then I have my reinforcing bar, and I just draw a section of this thing. If I heat this thing uniformly, then the concrete's going to expand a certain amount, and the steel's going to expand some other amount based off of these coefficients. If you remember back in your mechanics and materials class, this is that alpha factor for the thermal coefficients. And so if I heat this thing, the concrete's going to move a little bit differently than the steel, but not enough. Okay, and the bond is what exists at the interfaces between all of this. So it's not a major factor. Okay. Now, something else that the concrete does for us is that the alkali material that's present in concrete will prevent the steel from corrosion, okay, until such time as cracking occurs and water and chloride and those kind of things start to be introduced through channels. So what will happen is you'll have a bar, look something kind of like this, and then eventually you'll get some sort of crack that starts to form under there, and this becomes the entry point to be able to damage causing the bar. Reinforcing steel inside of concrete without cracking is generally pretty safe, right? There's an alkali layer that forms, and that there's no corrosion that will exist on the bar. Okay. Let's see. We've got also that the low conductivity of concrete will protect the steel from fire damage. All right. So concrete is a very good insulator for heat. So if I have a fire outside of this, now I might get a little bit of spalling because that heat will affect steel differently than concrete. And if this distance becomes too small and my steel heats up, I can actually pop off the outer edge of the concrete. But heat doesn't move through concrete very like it does move through steel. So that's kind of a cool feature. Right. And then the last one that we have is that the steel and concrete have good chemical bond. Okay. And so what will happen is the shrinkage of concrete actually helps the frictional bond. Okay. With the form bars, while the large mechanical bond is also assured. So again, we talked about the rebar having these ribs on it like this. Then when I pour the concrete around it, as the concrete tries to shrink, it locks in on the ribs that are down there. And I just went off the page. I apologize for that. So here's my rebar with the ribs shown on it, and I pour the concrete around the outside of this thing, and as it starts to shrink, it starts to push on these guys, which then helps to reduce the amount of strain that the concrete wants to undergo, that the bars actually help to kind of prevent it from shrinking too much and developing those tensile cracks. So this reinforcing steel for shrinkage is very, very important as we start to kind of look at that. So with that, I think we've got a pretty good handle on our material properties. Okay, so we've covered concrete in pretty good detail. In this lecture, we talked about creep and shrinkage, and then in the steel, we talked about some of the other characteristics, the stress strain characteristics as well. So with this, we should be ready to start to kind of do some simple strength calculations beginning in the next video. And so we'll look to do that. So again, as always, if you'll take a look at leaving a comment for us or tossing us a like on the video, that would really help us out. Subscribe to the channel, and you'll find out when more videos are being posted. We're going to continue to keep working on this and keep building up this library as a resource for the ACI 318 2019 code. So anyway, thanks for your attention. Have a great evening. Happy engineering.